Right now, in a laboratory in Harbin, in Northeast China, bamboo fiber is being dissolved down to nothing. Not shredded, not melted. Dissolved molecule by molecule until the plant loses its shape entirely and becomes a thick, honey-like liquid. Then something stranger happens. That liquid gets rebuilt from the molecular level up into a material that bends like plastic, snaps into a mold like plastic, and resists heat better than most plastic on the market today. And then, buried in ordinary soil, it disappears completely in under 2 months. Somewhere on this planet right now, a factory is producing a piece of plastic packaging that will still exist, mostly unchanged, in the year 2500. This video is about the material scientists believe could make that packaging obsolete. Stay with this, because the number behind how strong this new material actually is will surprise you. This is not a concept video or an artist's rendering of some future material. This is published, peer-reviewed research that came out on October 7th, 2025, in the journal Nature Communications, one of the most respected scientific publications in the world. The work was led by materials scientist Haiping Yu at Northeast Forestry University in Harbin, in collaboration with Dawei Zhao at Shenyang University of Chemical Technology, with funding support from the National Key and the National Natural Science Foundation of China. This is not a press release dressed up as science. It is a fully documented, methodologically transparent study with the raw data available for other scientists to check. To understand what these researchers actually did, it helps to picture the inside of a plant cell the way you'd picture a brick wall. Bamboo, like all plants, gets its strength from cellulose, long molecular chains that lock together through countless tiny chemical handshakes called hydrogen bonds, the same way individual bricks lock together through mortar to form a solid wall. T-hat wall structure is exactly why raw bamboo fiber is strong, but it is also why earlier attempts to turn bamboo into plastic kept failing. You cannot easily reshape a finished brick wall into something new. It just cracks and crumbles. Scientists needed a way to take the wall apart, brick by brick, without destroying the bricks themselves, and then rebuild it into something even stronger than the original. Here's the number worth sitting with before we go further, because it frames the entire stakes of this story. Global plastic production is projected to reach 1.23 billion tons per year by 2060. To picture that scale, imagine a mass equivalent to more than 3,000 fully loaded aircraft carriers, produced not once, but every single year, forever, unless something changes. Now picture that same tonnage stretched across time instead of weight. Even if the world stopped producing plastic today, the material already sitting in landfills and oceans would still be breaking down, slowly. Centuries from now, while your great-great-grandchildren deal with fragments of it in the soil. That is the scale of the problem this Harbin lab set out to chip away at. Here's how they actually took the wall apart. Yu and Zhao's team submerged bamboo fiber in a solution made from zinc chloride and formic acid, a combination chemists call a deep eutectic solvent. This solvent doesn't just soak the fiber, it methodically breaks the hydrogen bonds holding the cellulose structure together, dissolving the plant into what the researchers describe as a homogeneous molecular system, essentially a uniform liquid where every long cellulose chain is now free-floating and disconnected from its neighbors. During this process, some of the fiber's chemical groups swap partners with the formic acid, attaching new formate groups onto the cellulose chains, a subtle modification that turns out to matter enormously for what happens next. This step alone represents a departure from how earlier researchers approached the same problem. Previous attempts to make bamboo plastic generally relied on extracting cellulose fibers and then physically compressing them under heat, essentially hot pressing the plant. Material into a new shape while keeping its underlying molecular architecture mostly intact. That approach preserved some of bamboo's natural strength, but it also preserved bamboo's natural brittleness, producing materials that could handle a straight pull but shattered under bending or repeated stress, with elongation rates before breaking of 5% or less. Yu and Zhao's team took a fundamentally different route by going all the way down to the molecular level first, accepting that they would have to destroy bamboo's original structure completely in order to build something better in its place. Quick recap before the reveal, because this is the moment the strategy pays off. Bamboo's natural strength comes from a locked hydrogen bond structure. That structure resists reshaping, which is why earlier bamboo bioplastics kept turning out brittle or weak. Yu and Zhao's team dissolved that structure entirely using a zinc chloride and formic acid solvent, reducing bamboo to a liquid molecular system, then modified the chemistry along the way so the cellulose chains were primed to reconnect in a denser, stronger configuration. The question was whether that reconnection would actually work. It did. After forming an intermediate gel using calcium chloride, the team treated it with ethanol, which triggered the cellulose chains to snap back together, this time forming far denser, far more ordered hydrogen bonds than the original plant ever had. X-ray analysis of the material before and after this ethanol treatment showed the structure shifting from a broad, disordered pattern into sharp, distinct crystalline peaks. Direct physical evidence that the cellulose chains had reorganized themselves into a tighter, more efficient arrangement than raw bamboo ever achieves naturally. Here's the part that changed everything. The resulting material, which the team named BM plastic, short for bamboo molecular plastic, achieved a tensile strength of 110 megapascals. 110. That number alone puts it ahead of polylactic acid, or PLA, one of the most widely used commercial bioplastics on the market. And it holds its own directly against petroleum-based plastics like ABS, PMMA, and PA66, which are used in everything from car dashboards to phone casings. The material's flexural modulus, a measure of how well it resists bending without permanently deforming, reached 6.41 gigapascals, and it maintained its shape and toughness at temperatures above 180 degrees Celsius, a threshold that causes many conventional plastics to warp or grow brittle. In dynamic testing that pushed the material through a range of temperatures, BM plastic held a usable structural stiffness even past 150 degrees Celsius, a range where several conventional plastics have already begun to soften and lose their shape entirely. If you've made it this far, you already know this channel goes looking for the science behind the headlines most people scroll past. So go ahead and subscribe now, because the part of this story about what happens when you bury this plastic in the ground is where it gets genuinely strange. That confirmation came directly from the material's behavior, against materials scientists already understand deeply. When the Harbin and Shenyang team ran side-by-side comparisons, BM plastic didn't just survive against conventional engineering plastics like ABS and high-impact polystyrene, it beat them across several measurements simultaneously, including impact resistance, where it registered a strength of 110 kilojoules per square meter. Independent reviewers who examined the work, including polymer chemist Andrew Dove at the University of Birmingham, described the achievement as evidence that sustainable, bamboo-derived materials can genuinely perform at the same structural level as the petroleum-based plastics people have relied on for the last 70 years. That kind of outside validation matters, because materials science has a long history of lab-scale breakthroughs that look impressive on paper and then quietly fail to hold up under independent scrutiny. This one, so far, has held. Now here's the part that connects everything back to the plastic sitting in your kitchen drawer right now. The researchers didn't stop at strength and heat resistance. They buried strips of BM plastic in ordinary garden soil, alongside strips of ABS, high-impact polystyrene, PA66, PMMA, PLA, and PBAT, the last two being existing commercial bioplastics already marketed as biodegradable. After 50 days at room temperature, the BM plastic had completely disintegrated, broken down by ordinary soil microbes into nothing detectable. The conventional petroleum plastics showed essentially no degradation at all. Even PLA and PBAT, the bioplastics already sold today as the eco-friendly option, only partially broke down in that same window. 50 days, that is not a rounding error. That is the difference between a material that vanishes within 2 months and materials that, by some estimates, can persist in the environment for hundreds of years. There's also a question worth sitting with here, because strength and biodegradability usually work against each other. Making a plastic that degrades quickly typically means making it weaker and less durable, and making a plastic tough enough for real industrial use typically means making it resistant to the exact microbial and environmental forces that would ever break it down. BM plastic appears to sidestep that trade-off almost entirely, and the team's explanation for why comes down to the very structure that gives it strength in the first place. The dense, ordered hydrogen bond network that makes BM plastic strong is built from natural cellulose chains, the same organic material every microorganism on the planet has spent hundreds of millions of years evolving the enzymes to break down. Petroleum-based plastics resist microbial digestion precisely because their chemical structure is so unfamiliar to biology. BM plastic keeps a structure biology already knows how to dismantle. It's simply organized more efficiently within that structure. In the next part of this, it's worth looking at whether this material can actually survive contact with the real world, not just a laboratory bench. The team tested BM plastic against moisture, submerging samples in 90% relative humidity for 48 hours, and in liquid water for a full day, and the material retained meaningful tensile strength in both cases. They tested it against a battery of harsh solvents, including dichloromethane, tetrahydrofuran, methanol, strong acid, and strong base, over a full week, and the material held its shape without swelling or disintegrating. They also demonstrated that BM plastic can be shaped using the exact same industrial techniques already used for conventional plastics, injection molding, casting, and machining, producing everything from small gears and shells to full-sized honeycomb panels measuring 50 centimeters across. That last detail matters more than it might sound. A material that requires an entirely new manufacturing process to use is a material that stays in the lab. A material that slots into equipment factories already own is a material with a real path to a factory floor. There's a recyclability angle here too, and it might be the detail that carries the most weight for long-term adoption. A material that can be dissolved, reshaped, and reused while barely losing performance closes a loop that conventional plastic manufacturing has never managed to close at scale. The same underlying solvent chemistry that builds the plastic in the first place also unbuilds it on demand, which means, in principle, a single batch of the zinc chloride and formic acid solvent doesn't have to be thrown away after one use. The researchers describe recovering and reusing the solvent itself as part of the overall production loop, precipitating out the calcium ions used earlier in the process and distilling away the ethanol, leaving a solvent ready to dissolve the next batch of bamboo fiber all over again. Quick recap, because there's a lot stacked up at this point. Researchers in Harbin and Shenyang dissolved bamboo cellulose down to its individual molecular chains using a zinc chloride and formic acid solvent, then rebuilt those chains into a dense new structure using ethanol. The resulting BM plastic matched or beat major commercial plastics in strength, heat resistance, and impact toughness. IT fully biodegraded in soil within 50 days, something no comparable commercial plastic managed. And it can be recycled and reshaped while keeping 90% of its strength, using manufacturing equipment industries already have. The final piece of the puzzle is whether any of this can actually be produced cheaply enough to matter. According to the team's techno-economic analysis, producing BM plastic at scale would cost approximately $2,302 per ton, landing squarely between the cost of conventional plastics like PMMA and PA66 on one side, and existing commercial bioplastics like PLA on the other. The largest share of that cost, just under 38%, comes from raw material sourcing, with another substantial portion tied to the reusability of the chemical solvents involved. Electricity, notably, made up only about 3% of total production costs, a detail the researchers highlighted as evidence that the process itself is relatively low energy compared to many industrial plastic manufacturing methods, which often require sustained high heat and pressure that BM Plastic's room temperature chemistry simply doesn't need. Bamboo itself helps the economics considerably. It is one of the fastest growing plants on Earth, capable of producing up to 78.3 tons of biomass per hectare, more than 4 times what traditional timber forestry yields on the same land, and it requires no fertilizer, no pesticides, and doesn't compete with food crops for farmland the way corn-based bioplastics sometimes do. Now for the part that has to be said plainly, because a discovery this promising deserves honest limits, not just excitement. This is a single peer-reviewed study, not a finished commercial product sitting on a store shelf. The researchers themselves are explicit about this. Large-scale industrial production, extensive real-world testing beyond laboratory conditions, and formal market, or regulatory approval are all steps that still lie ahead. And the paper describes the work as an early-stage demonstration of feasibility rather than a launch-ready technology. The 50-day biodegradation result came from controlled soil conditions at a steady 25 degrees Celsius. It says nothing directly about how the material behaves in a landfill, where oxygen and microbial activity are often far more limited, or in ocean water, a separate and much harder environmental challenge that has defeated plenty of other so-called biodegradable materials before. Greenpeace researchers in China have already raised exactly this kind of concern about the country's broader push into biodegradable plastics, noting that materials marketed as eco-friendly often still require specific industrial composting conditions to break down as advertised, and that without the right infrastructure in place, biodegradable plastic waste can end up sitting in ordinary landfills for far longer than headlines suggest. That is not a criticism specific to BM plastic, but it is the exact kind of gap between laboratory promise and real-world outcome that this technology will eventually have to close. And matching bamboo cultivation to a meaningful fraction of that 1.23 billion ton global plastic demand would require a scale of land use, harvesting, and processing infrastructure that does not yet exist anywhere in the world. Promising lab chemistry and a functioning global supply chain are 2 very different mountains to climb. And this research has only climbed the first one so far. It's also worth being clear that Yu and Zhao's team is not working in isolation, and this matters for how much confidence to place in the underlying science. Other research groups have been chasing very similar goals with bamboo and other plant fibers in recent years, including a 2024 study in the journal ACS Nano. that converted bamboo into a strong, waterproof, biodegradable plastic through a different structural approach. An earlier work published in Chemical Engineering Journal exploring bamboo-based plastics, stabilized through different chemical bonding strategies. None of those earlier efforts matched BM Plastics' combination of strength, heat, resistance, and fast biodegradation all at once. But the fact that multiple independent labs are converging on bamboo cellulose as a serious plastic alternative is itself a meaningful signal. This is not one team chasing an isolated result. It's a genuine active front of material science, and it fits inside a much broader pattern already visible across China's manufacturing sector, where separate research groups have also been pushing bamboo fiber into aerospace composites and industrial cooling systems, treating the plant less as a traditional building material and more as a genuine engineering substrate. Peer reviewers on the BM Plastic paper itself, including 2 anonymous specialists in polymer science who evaluated the manuscript before publication, raised no objections to the core findings, which is a meaningful, if less headline-grabbing, form of validation in its own right. And if the idea of watching a real scientific breakthrough get explained clearly, without the hype and without the doom, is why you're still here, that's exactly the kind of video this channel exists to make. So if you haven't already, hit subscribe, because there's more of exactly this kind of story coming. So picture it once more, a piece of bamboo harvested from a hillside somewhere in southern China, growing so fast it could climb nearly a meter in a single day, dissolve down into a liquid so uniform that not one of its original cellular structures remains recognizable, then rebuilt atom bond by atom bond into something stronger than the plastic in your phone case, tougher than the plastic in your car's dashboard trim, and capable of vanishing back into the earth in less time than it takes most people to finish reading a novel. The plastic problem the world is facing was never really a problem with the concept of plastic itself. It was a problem with plastic's total refusal to ever leave. What you, Zhao, and their colleagues built in that lab in Harbin is a version of that same convenience, minus the permanence. And if it scales the way early signs suggest it might, the plastic waste piling up in landfills and oceans today may eventually be remembered as a problem, this century solved rather than one it simply left behind.